My name is Adam Bertsch. I work at Lawrence Livermore National Laboratory, and I'm our integration project lead for the Sierra Supercomputer. So this is the corollary to the Summit machine you heard about in the keynote. And this is my real title slide, because it made me change it, but it has all the legal mumbo-jumbo from the lab on it. I'm going to talk about a couple of different things. I'm going to give a short introduction to the Sierra computer itself, and you'll get a lot more technical information about the platform in Chris's talk at the end of the day, so make sure you stay for that. And I'm going to talk kind of a lot about the collaboration that is really the key to making these computers work. Now, for me, the Sierra Supercomputer started at kind of an odd place. Riding my bike with one of our computer center directors and talking about, what was my career and my job going to look like in the future, because I've been doing this admin thing for a long time, and what comes next. And I said, well, we're going to do this pre-exascale computer in a few years, and that might be a thing. I was like, what's a pre-exascale computer? Is that like not really a computer? But it turns out that it's it's just the next generation of machine for us. So advanced simulation and computing is the program at Livermore that's responsible for the computer systems that we use for stockpile stewardship. Stockpile stewardship is ensuring the safety, security, and reliability of the United States nuclear weapons stockpile, but without the reliance on nuclear testing. So instead of doing this really ugly, messy thing of blowing up nuclear weapons, we do that in the computer. And there's some significant advantages to doing that in the computer. There's other kinds of simulations, of experiments that you'd rather do in the computer, but this is probably like the canonical example of the thing you really don't want to do in the outside. So we have our current generation platform, which is Sequoia. That's an IBM Blue Gene Q system. And you can see we alternate with our partner labs, Los Alamos and Sandia, with these advanced technology systems platforms. So these are our platforms that are not just pizza boxes, InfiniBand, and Go. We're going to try to innovate with a very large platform, typically one or more advanced technologies that you can't find in the commodity market yet. So things like NVLink, right, show up in these platforms. And the last bit of interestingness on this slide, I guess, is that we did extend the life of Sequoia out, so we'd have significant overlap with Sierra, so that people can port, right? The previous platform, Sequoia, was just massively parallel, homogeneous system, and now we have this heterogeneous computing world that we're talking about at this whole summit. So here's what our system looks like. Every compute node has 4 Voltas in it, 2 Power 9 CPUs. We have 256 gigs of memory in each node, which I'll talk about in a little more detail later, how we ended up there. We also have the HBM2 on each GPU, same rack layout as the Oak Ridge system we had in the keynote, and then we're going to have 4,320 nodes, and that means that we're at about 12 megawatts. And so that's actually a really disruptive bump on the power performance curve for us, right? Sequoia, which is only a 20 petaflop computer, was about 10 megawatts, so we haven't really raise the amount of power that we have to use, and we've gotten this huge bump in performance. So that's great. The bad news is that for an exascale system, we don't necessarily see another huge bump in the power performance curve, so we're going to need a lot more electricity for the next generation. We do have a spectrum scale file system, and that's 154 petabytes, and we have a slide on that a little bit later. So this is a major shift for our application teams. We were very much on the MPI everywhere, homogeneous system bandwagon for a very long time. Our applications are very complex, millions of lines of code, lots of data movement. Very hard to look at the traditional accelerator model where you're transferring all that data over the PCI bus and say, oh yeah, we can do that. It was more, no, we can't possibly do that. And so we had been very much on this MPI everywhere homogeneous curve. And then we said, well, that's not going to make it, right? That curve we've been riding for so long isn't going to get us to the next generation, not inside the power envelope that is, conceivably doable with a data center and that kind of thing. But there's this idea of NVLink and unified memory that will solve all of our data problems, or at least make them a little bit tractable. And so that's where we are. We've taken this 180 turn, and we're doing GPUs now. Oak Ridge was on the GPU bandwagon a little earlier than us, so they have some more experience. But we looked at this whole thing and said, we are going to have to change radically, and we don't know what the next architecture is going to look like. We don't know if it's going to be just like this, or if it'll have some other kind of accelerator. Is it going to have FPGAs? So our codes really started to evolve, not just the codes, but a lot of tools and abstractions, and we started years in advance this time. We took the Center of Excellence concept that Oak Ridge had used on Titan, and we've really made that the basis for how we evolve our codes to go forward. And that's really what we're hanging our hopes on, is being able to continue to use these abstractions that we developed. So we did make some cost-neutral trade-offs in the architecture. We got hit by this, DRAM actually cost twice as much as we thought it was going to cost in this time frame. And we made some choices, and Oak Ridge made some choices, and that actually has caused the appearance of our machines to diverge more than we had originally planned. We have a pretty fixed budget, so our choices had to be cost-neutral. And we had two options. We can buy half as much memory. That's an easy way to deal with the fact that it costs twice as much, right? Or we can take a hit somewhere else on the system. And what we did figure out was we could taper the network. Half as many top-level director switches and half as much bandwidth going up to them, that would have about the same cost impact, and we could make that work. And then we did a bunch of performance analysis about what's going to happen to our applications if we make these choices. And it turns out that neither one of those choices was going to hurt our applications too much, so we selected both options. And that means we get about 5% more nodes, because we saved some money there. And for the workload that we're expecting to take up most of the cycles, that's only going to have a performance loss of about 1% node over node. And by getting 5% more nodes, we actually get more performance out of the computer. So this is what our systems are going to look like. Sierra, which is the big system. And we also have an unclassified system. We're currently calling it USierra, but that's not going to be its final name. And then we have another environment called our RZ environment, which is another unclassified environment where we do some development. And the important thing to note here is that even though Sierra is going to be classified and people aren't going to have an opportunity to use it if they're not part of certain programs, we do have a significantly sized, unclassified, open science platform in USierra. And it is exactly like Sierra, it just has fewer compute nodes. Now, when you do one of these procurements, you are setting some targets that are kind of shots in the dark. You're like, hey, it would be nice to get these things because we'd like to evolve the applications to get to a certain place. And then you go and talk to vendors and you evaluate proposals, and usually you don't get everything you want, right? You have to make some trade-offs. And in this case, we did not have to make very many trade-offs. The proposal, even though it was completely different than what we were kind of expecting for our next generation system, what we had envisioned when we put the proposal out there, what we got back is basically everything that we wanted, except in the case of Livermore, we don't have aggregate of 4 petabytes of DRAM, partly because of the memory costs, and partly because we had envisioned a system with a much higher node count, and therefore you would end up with a ton of aggregate memory just as a way to have enough memory per MPI task. But we ended up with way more memory per MPI task than we were going to need. So we ended up with just a really great system. So let's talk about the collaboration that got us there. So you heard a little bit about Coral in the keynote. Collaboration of Oak Ridge, Argonne, and Livermore. And so we first of all collaborated on our requirements. We have slightly different requirements, each of our computer centers. And typically that has led us to do separate procurements. But what if we look at what we have in common? And it turns out we have almost everything in common. So that's one layer of collaboration, is just on the requirements. And then by putting out a procurement where we were going to buy multiple systems and guarantee we were going to pick multiple vendors. That means it doesn't have to be just one winner, right? The ecosystem can be funded in a number of different winners. And that hopefully gives some incentive for people to actually bid, right? Because it costs a lot to respond to one of these huge procurements for a leadership class supercomputer, right? There's a lot of investment that goes in from the company. So they need to feel like there's some chance they're going to win before they make that investment. So we said we're going to award 2 build contracts for 3 systems and 2 NRE contracts. So those are, NRE is non-recurring engineering, where we say, we need to develop these technologies to make the computer a success, and we're just going to fund those technologies, and your deliverable is a report that says you created the technology, even if we never buy the computer. And that's another way for DOE to accelerate HPC. Now, another place where we have a bunch of collaboration, and this is where OpenPOWER comes in, is on the vendor side. It used to be that we would get these, monolithic build contracts for one vendor to bring everything to the table and make it happen. And we still have a prime contractor, right? IBM is a prime contractor for our systems. But it's no longer necessary that IBM has to do in-house engineering to create every single piece of the system. It's just too complicated. There's too much going on, especially with accelerators, right? There are companies that do accelerators really well. There are companies that do interconnects really well, so we don't have to have one vendor bring everything to the table anymore. And if you see here, we've got in OpenPOWER, we have IBM, Mellanox, NVIDIA. This is a slightly older graphic, but Red Hat is in the new graphic, right? All of the major players for the core systems are all part of OpenPOWER. And without the collaboration and the cooperation and the IP agreements in place for OpenPOWER, they wouldn't have been able to do this. So the NRE, there's a bunch of areas that we wanted to accelerate technology, but the thing that came out of the NRE that was most critical to me is not even just these technologies, but these working groups that were around to feed into the technology proposals, evaluate the reports that came out. And even though the NRE contract is basically over now, right? Technology has been created. All of the working groups are still together, right? All of those working groups have just transitioned from an NRE working group into a system deployment working group with the same portfolio they started with. So this is another place where collaboration is the only way that we're able to have success with these systems. So a couple examples of success in each of these collaborations. So the file system working group came together, and the original plan of record had a pretty capable system. And in particular, we had concern about metadata performance on a really large file system. GPFS has some areas it's really strong in and some areas that at the time it wasn't as strong in. And one of those areas it wasn't as strong in was metadata performance in creating a bunch of files in a single directory, right? Single shared directory performance. And so we invested a lot of time, money, energy into accelerating that development. And at the same time, you're offering up a hardware solution that looks like this. When there's some newer stuff out there on the market that might be better for everybody. And this is an area where Oak Ridge really went out and did the heavy lifting on this and said, we think we can do better on the storage solution. And IBM came back with, at the same cost, significantly more space, significantly more performance, and we did have success with getting all of that code into GPFS. So that's an area where this close partnership and this collaboration really led to improvement of this whole ecosystem in the storage space. Another place that the collaboration was just key is in the proposal. We always put out these benchmarks, right? You can't really evaluate performance on really big apps, but you can take some benchmark codes and you can try to predict what they're going to perform like on an eventual system. And in this case, we had IBM with their Power 9 and NVIDIA with the Volta GPU, neither of which existed in 2014 when we signed this contract, right? But we needed to know how they were going to perform and have a believable story that says if you invest in this technology, real apps that you care about will perform. And so, OpenPOWER and the agreements in place between NVIDIA and IBM allowed them to collaborate incredibly closely to get there, right? To not only predict how well applications might perform on the potential architecture, but then to follow through over the next 4 years and actually hit those targets. The amount of credibility that they were able to carry forth is a big reason why they ended up winning the contract, and the fact that they were so credible and then so successful in bringing the advertised performance to delivery is just really exciting. And without the ability to collaborate like that, it just can't happen. You can't have IBM say, well, we think the GPU guys might make it work, and the GPU guys going, sure that the CPU guys will feed us the data we need, and then just buy the computer, right? You really need this collaboration to make it happen. So when we do these things, we always buy some sort of early access system so that we can get going with our application teams ahead of time. And it also provides a good checkpoint that the technology is moving in the direction it needs to move to get to the big system in the time frame that the big system is going to be delivered. So both Livermore and Oak Ridge purchased early access systems based on the Minsky server with 4 Pascal GPUs instead of Voltas and 2 Power 8 processors instead of Power 9s. NVLink, similar kind of big memory footprint. And we also got really early access to a bunch of the technology. Beta compilers being probably the biggest one, right? The compiler story for heterogeneous architectures is a tough story. It's far from a solved problem. And so that was one of our big concerns coming in, is what's your compiler story, and how are we going to know if that story is going to work in a time frame that we can still bail out if it's not going to work, or make significant changes to the program so that it will work. And so that's really what this is about. And we had all the components there, right? Very similar kind of rack and physical layout, early access to the file system technology. Everything is there, and everybody is actually running on these systems today. And codes have really come a long way for us. We did buy 3 of them, right, for our 3 environments: the open, the kind of open science environment we call the CZ, the RZ, which is our slightly more restricted unclassified environment, and the SCF, our classified environment, where the real work of the program is going on. And so people in all of those places were able to get there. So this is the beginning of an accelerator-based era of computing at Livermore. We are making a big change from where we were to where we think the industry has to go to continue to perform, for all the reasons that the keynotes we were watching this morning kind of covered. Power efficiency is really important for all of us. You can only bring so much electricity into a building. You can only cool so much footprint, right? There are some significant network advantages to having these really big nodes. You don't have to have nearly as many endpoints in your network. That's a much simpler place to come from. So that was an advantage for us. There are some downsides to the super large nodes, though. You need more bandwidth per node. So that's a trade-off that has to be considered. The most important thing, I think, was that there was a clear path for performance portability, that by creating abstractions, software abstractions for defining where the parallelism lives in your code, and then porting our codes to those abstractions instead of porting our codes directly to something like CUDA. That means that we can still run on CPU machines, we can run on GPU machines like this, and we can run on whatever's going to come out tomorrow by plugging in a new backend to our portability layer. Without that, we could not have convinced our applications teams to make the investment in this kind of a system. We have really complex memory hierarchies, and it's important for us to have some sort of defined way to interact with those hierarchies to get performance out of the system. The current accelerator model, we have a very clear understanding of where you need to move data. You want to leave data in the accelerator as long as you can, and then move it back out. This was an understood model already. We didn't consider that a big risk, whereas some of the other models we considered, there was a lot of, there's a complex multi-level memory hierarchy and magic. And here, at least, we understood what was, what was going to go on. I think the most important thing for systems going forward is that we all continue to and increase our collaboration, right? Continue to collaborate and increase collaboration. On the vendor side, everything is too complex, right? There are too many areas of technology with too much exciting stuff going on for any one company or platform to have all the answers. So by collaborating and sharing information, we can get there, right? So you have NVIDIA and Mellanox and IBM in this case, and on the procurement side, having multiple laboratories share in the burden of creating these procurements and getting all the right requirements, and frankly, learning how some other people are doing this, right? Like at Livermore, we've been doing big HPC procurements for a long time, and we've got our way of doing it, right? And Oak Ridge has been doing it for a long time, and they had their way of doing it. And being able to learn from each other has just been really powerful and given us both, better systems that we are better prepared for than we would have otherwise been. So this really, we think it represents a very viable path to exascale to go with an architecture like this, and that's really what a pre-exascale computer is about, is do we have a path that's going to get us where we want to go? Now, I do have a time-lapse video that covers the first quarter of our system integration. And I'll go ahead and run through this. Our system and the Oak Ridge system are still under integration right now. But this is pretty cool, because you can see it starts with a giant hole in the floor and lots of water and cable tray and power. And then, we're collaborating with our facilities teams and operationally, so we're actually starting to site the infrastructure of the system while the hole is still in the floor, right? I mean, this is the only way to make the schedule for these kind of things work. You've got to start the facilities, months and months and months in advance. Now you can see compute racks showing up, and those racks show up empty in this case, and then we fill them with compute nodes. Now there are some differences. So we had the giant hole in the floor, so we had to get all that stuff in before the computer showed up. Oak Ridge is on a slab, right? So they did the opposite. They have everything coming in from the top, and the computer starts underneath it. And I think it's a testament to the flexibility of the solution that both of those things can actually happen with pretty much the exact same hardware. So you can see we're starting to power on systems in the back there.
How high up is that ridge floor?
It's about 4 feet deep, and it is full, right? It's pretty much immutable at this point. There's an amazing amount of CAD and design that goes into layering, the water and the power and the cable tray and everything. There is no space, there's no crawling, right? It is completely full of infrastructure now. Yeah, Chris. So floor loading is definitely a thing, right? This floor is half as strong as our newest floor because everything keeps getting heavier. So yes, there are concerns. On Sequoia, which had a really heavy compute rack, we actually had to build these giant steel platforms and replace the section of floor with these platforms that actually sited the racks. This system is actually a little more kind on floor loading, it turns out. You also may have noticed that there's a bunch of platforms that went underneath these racks before they went down. That's because we're in California, where sometimes the ground shakes. And so those platforms are actually kind of like a large building where it has a big old ball bearing in a concave dish, and so it allows the floor to move while the computer stays still. So that's what that's about. So I think I have just time for a couple of questions, pretty much right on time. Does anybody have any questions? Well, so that time lapse goes from like July, when we started the facilities work, through the end of December, when we finished the 25%, the first 25% of the system was accepted. And then we'll have another one that will cover the whole thing. That's kind of a rough edit. We usually try to make them cleaner than that, but this is where we were at. So 4 or 5 months. Yeah.
What's your plan for your early access systems going forward? How long are you going to operate them, and you have a specific role for them after Sierra comes online? What are you going to do with them?
So we made a significant investment in early access systems, right? Those are, one of those is like a petaflop resource, right, Ray? So we're going to do a couple different things with them. One is we really want to get the software environment on them to be the same as the Sierra software environment. And we have not quite closed that yet, I think is a fair statement. So we want that environment to be the same so that people can port back and forth as easily as possible, not just their codes, which are already pretty much completely portable between them, but also their run scripts and all that kind of ancillary software plumbing that allows you to actually run on an HPC system. In the case of Ray, we got a little extra money to do some data-intensive computing work on that machine, so we were able to make it a little bigger. So it's going to also transition into doing a lot of data-intensive work, right? So we're heavily biased towards the, physics, molecular dynamics, multi-physics, simulate the real world problem space for the ASC program. But Livermore is a big multidisciplinary lab, just like Oak Ridge, and there's people doing all sorts of different stuff. So we're going to definitely use them for some of that other work as well. Anything else? Yes, sir. Yeah, so the question was about running the Blue Gene custom CNK microkernel versus the full Red Hat, basically commodity kernel on Sierra. And from a purely technical perspective, there were some great things about the CNK, right? The run-to-run reproducibility in terms of performance and expectations with that microkernel was near perfect. So when people would make changes to their code and run performance studies back to back to see whether they had improved or not improved things, it was very, very easy for them to make very accurate comparisons between the old and the new. It also meant that we were able to keep OS noise to a near zero level. In fact, some guys from Argonne did a study on a Blue Gene where they basically considered the Blue Gene to be a zero noise environment and injected false noise to look at what the performance implications were to an MPI application. Now on Sierra, we have that kind of normal, slightly noisy system. And so we've had to make some big technology investments in trying to reduce OS noise. And I think that both computer centers are planning to set aside some cores just for OS tasks in order to reduce the impact of noise. I think it's kind of it's an ongoing area, exactly how many cores we're each going to end up setting aside, and whether users with applications will be able to select how many cores based on their application needs, balanced against like their I/O performance needs, which GPFS has to do a lot of work and therefore can create noise, right? Those are compute cycles that aren't going to your application if they're going to GPFS, right? As far as the movement of the technology, for better or for worse, the Sequoia system started with a particular set of function and system calls and environment, and it pretty much didn't change. So the good news is, if you were able to run on day one, it still works today, 6 years later. You can't really underestimate how valuable that is to an application team. On the other hand, some of our abstraction layers rely on C++ 11 and 13 and 15 features, right? And we don't get any of those features in Sequoia because the software stack is frozen 6 years ago, pretty much. So there are upsides and downsides. Whereas the Red Hat stack on Sierra has everything that Red Hat has in it, and it continues to move with Red Hat. So I can't say one is better than the other. They're different, and there's very real reasons to make both choices.